Assalamualaikum. My name is Muhammad Iman bin Muhammad Bayhaqi, and today I'm pleased to introduce our session on project management under the guidance of Professor Madya T.S. Dr. Haji Muhammad Haji Makno from the Faculty of Mechanical and Automotive Engineering at UMPSA. Let's start with core question is what is a project? A temporary mission with a specific goal, a start date and end date. The triple constraint. A project success depends on balancing scope, time and cost. The five P's of project life. First is initiation, planning, execution, monitoring and control, and lastly is closure. To guide us through this discipline, here is our course blueprint. We break the material down into six distinct modules. We begin with the core framework, establishing our strategic alignment, the project charter, and the fundamental differences between operation and project. From there, we systematically advance through the five project lifecycle. Is phase one, we tackle initiation process like feasibility and stakeholder matrices. Phase two, move into advanced planning tools, including work breakdown structures, WBS, and the critical path method, CPM. Phase three focuses on execution control team, dynamic and procurement. Phase four, introduce quantitative control via and value management (EVM), and finally, phase 5 address contract closeout and building a lesson learned database. Strategic engineering alignment, bridging strategy and operation. Modern engineering project cannot exist in isolation. Every mechanical, industrial, or system design initiative must map directly back to organizational strategic objective. Portfolio management secure optimal resource usage, structure risk modeling prevent catastrophic failures, and continuous design feedback loops and ensure market fitness. Project versus business operation. Project unique and temporary. A project is a distinct, not repetitive endeavor with a strict beginning and end. Operation, continuous and routine operation are ongoing, standard organizational processes designed to sustain the business day to day. The traditional triple constraint, balancing quality equilibrium. Every project operates within these three fundamental boundary conditions: scope, time, and cost. Project initiation. Initiation step 1, feasibility analysis. A technical feasibility investigating if existing material, science, processing equipment, engineering tools support design target. Economic feasibility, calculating preliminary return on investment ROI, and others. Legal and regulatory compliance, reviewing alignment with global standard organization ISO, ASME, and national environmental acts. Operational viability, verifying standard workplace alignment, localized supply chain stream, and immediate maintenance capacities. Initiation and step 2, stakeholder assessment. For high power, high interest in individual like our sponsor and executive board, we manage them closely with continuous update. For technical regulator who hold high power but low daily interest, our model is to keep them satisfied via rigorous compliance review. Our engineering members have high interest but a lower individual organizational power. We keep them truly informed using operational daily stand-up meeting. And finally, the general public and neighbors fall into the low power, low interest quadrant, where we monitor them and provide periodic media releases regarding safety and noise mitigation. Step 3 is initiations. Initiation step 3, charter execution, formalizing project authority. The project charter represents the baseline contract of trust. It officially aligns board vision, secure early corporate capital, and assign formal leadership execution rights. Declare baseline business objective, formally names the project leader, and outline preliminary risk tolerance. Quantifying business value target. Target hurdle rate is 18%. So we need to setting the initiator hurdle rate. Net present value (NPV) must strictly exceed zero. Payback threshold goal of under 36 months. And internal rate of return (IRR) target above corporate average cost of capital. Project planning. Planning phase structure blueprint. First is work decomposition. Formulate the work breakdown structure (WBS) to slice scope into low-level engineering packages. 2. Logic sequencing. Develop critical path schedules, mapping all logical network dependencies and milestone constraints. Cost estimating. Accumulate package cost bottom up to build the approved baseline budget and contingency buffers. Planning step 1, decomposition. WBS structure decomposition. The will break down structure, deconstruct the complete the scope of project effort into deliverables. It does not map timelines but identify clear engineering outcome. Work package execution. The lowest component of any WBS is the work package. This level yields a clear measurable outcome that can easily be assigned to a specific engineer or subcontract. 2 is critical path method. Tracking scheduling chains. The critical path method (CPM) represents the sequence of dependent tasks that defines the minimum total time frame needed to complete the scope. Delaying critical tasks directly pushes the final delivery date. Non-critical paths hold positive schedule float. Fast-tracking compresses schedules by running tasks parallel. Mathematical model in scheduling. Calculating floating slack. To optimize resource allocation, project engineers must model the schedule flexibility, known as total float (TF). The metric identifies long a task can slip without delaying the final delivery. Okay, so the total float is LS minus ES, which is late start and early start, and second one is late finish minus early finish. Next, planning step 3, cost baseline setup. We have allocated 450,000 for direct labor monitor via weekly timesheet. Materials and tooling stand at 322,000 ringgit managed via milestone tracking. Subcontractors account for 180,000 ringgit under fixed price contracts. Finally, we have a factor in a contingency reserve of 95,000 ringgit for non-identified risks, giving us total cost baseline of 1,045,000 ringgit. This baseline represents our approved scope performance baseline, which we measure against moving forward. Project execution. First is work mobilization. Establish workspace, release date details, engineering brief, and coordinate design activities. Second is quality validation. Inspect output against technical requirement to verify structure integrity and design conformance. Third is continuous update. Deliver progress updates since with stakeholders and adjust workflow bottlenecks in real time. Next is managing execution resources. Dynamic workforce allocation. First, we need to prevent several task over allocation, resolve scheduling bottlenecks, and maximizes specialized engineering output. Tubman stages of team evolution. First is forming. Teammates define initial roles and establish high-level rules of engagement. Second is storming. Internal conflict arises as individual working style and design philosophies clash. Third is norming. Symmetry emerges. Agreements on design paths are made. Collaboration solidifies. Fourth is performing. A highly integrated engineering unit producing deliverables with high efficiency. Execution is the capability of translating strategic roadmap decision into operational reality and sustaining performance metric from UMPSA Executive Lecture Series. Procurement and sourcing contracts. Fixed price (FP) contracts. The scope must be clearly defined from day one. The seller assumes design risk, cost variation are borne by the contract, protecting client budget. Cost reimbursable (CR) contract. Seller are reimbursed for actual incurred cost plus a professional fee. Next is monitoring and control. First is metric tracking, track the project indicators. Two is change control, assess a potential schedule modification. And three is quality update, execute regular engineering checkout. Earned value management metric. So we have a plan value, earned value, actual cost, and cost variance schedule and schedule variant. So this is formula to calculate and the operational significance. EVM performance indexes measuring cost and schedule drivers. CPI over 1 means excellent cost. SPI SPI less than 1 indicate behind schedule target. Quality control and inspection. Maintaining compliance audits. Eliminates variance, verifies structured engineer, and guarantees safe and reliable operation. Change management workflow. Formal request. Every change proposal must be documented. Two is impact analysis, analyze impact. Three, board decision. The change board controls CCB formally approve, reject, or defer modification to design baseline. Project closure. Systematic handoff. Customer acceptance, admin archiving, and resource reassignment. Administrative handoff step. Final verification and validation, contract closeout, lesson learned workshop, and asset handover and archiving. Continuous improvement, lesson learned database, safe valuable execution cycle, standard process template, and retain institutional knowledge. Next is conclusion. Ultimately, our journey down to the road of excellent breakdown into two core takeaway. Structural mastery. Project management is not just a list of guidelines, have a feasibility and CPM to a value analysis and practical application blueprint. Apply this framework directly within FTKMA automotive and mechanical research project, building stable structures, reduce timeline risk, and ensure reliable delivery. To wrap everything up, project management is the bridge that translates strategic engineering ideas into functional real world assets. Thank you very much for your time and attention today. I would also like to express my sincere to appreciation to for Professor Madya T.S. Dr. Muhammad Haji Makno for his invaluable guidance throughout this framework. Thank you.